Okay, so hello everyone. Today we're going to talk about Newton's laws. In the last lecture, we started talking about this push and pull and the perceived gravity, and we said that whenever there's a push or a pull, the perceived gravity is in the opposite direction. We also looked into the centripetal acceleration. Today we are actually going to give a name for this push and pull. These are the forces, and I'm going to start with the first Newton's law. You can complete the section in your teaching book and reading book about Newton's laws and also about weight, which we're going to do either today or next time. I'm not going to give you formal presentation of the Newton's law. I'm going to actually try to discuss it with you in a more simpler way, and then you can look at the formal definitions in the book. So the first law says that if you have an object, and this object is traveling in one direction, then it will keep going in that direction unless if there is a force acting upon. So if this object is traveling from left to right, it would keep traveling from left to right. It won't change the direction unless there is a force that is acting upon that object. This is basically the first law of first Newton's law, which is against the daily experiences that we have, right? I mean, you can throw a ball somewhere and then you see that it actually makes some kind of a curvature. If you kick a ball on the ground, then after some time it stops, right? It doesn't go forever. And it can change direction as well. So this is not, in terms of the daily experience, it doesn't go well with the daily experience, but we can, we know that, or we assume that at the moment that because there's a gravity, there's a friction with the floor, then the motion has a different shape than what we expect. But we expect that if you have that object traveling in space, and there's absolutely no forces acting, no pull and no push acting upon the object, then it will just carry on in that velocity forever. So this is basically the first law. Can we prove this law? We can't. Would this law hold in every coordinate system or every system? That is not necessarily true. It would hold only in inertial system. So if the object, for example, if you actually if you are in the car and that car is accelerating, so the coordinate system is accelerating with you, you would feel the other objects actually accelerating towards you, but the other object would feel nothing. So there would be no force acting on the other objects if the coordinate system, that the reference system that we're taking is accelerating. So this holds as long as we have an inertial system where there are no acceleration, there are no forces acting on the system itself. The second law, which is known as F equals ma, or F equals m dv dt. If you think about a spring, for example, you put a mass on that spring, you pull it, so this is the relaxed length of the spring, it would start oscillating. But as you just put it in that position there, it wants to go back to the initial position, or in the direction of the initial position, the relaxed length, and that is the spring force. So there's a force in the system, and that force wants to restore the system to the initial relaxed condition. It is an experimental fact that if you put a mass m here in mass m1, let's say, the force would be equal to m1 times the acceleration. So this is the spring force. Let's write Fs A1. So this is the acceleration in the system. Now, if you take another mass, m2, which is different than m1, the force would be the same, right? Is the spring force is the same for that spring. It would be m2 A2, which means that m2 here equals to A1. It means that if I double the mass, then the acceleration would be half. If I take m 10 times larger, the acceleration would be 10 times smaller, because the force is the same whether you put mass m1 or mass m2. In other words, if you have an object, the change, this says the change in the state of the object, right? What is the state of the object? State of the object is the, let's say, the current velocity of the object. So if you change the state of the object, the rate at which the state of the object changes is proportional to the force acting upon the object. This is another way of describing the second law. Now, this is an experimental fact. You change masses here, you always have the same force, so the acceleration changes accordingly. It's an experimental fact, but it's not something that we can actually prove. Now, you might ask again, when would this law hold? Would it hold in any reference system? What do you think? Think about it a bit. Would it hold if you are in an accelerating reference system? No. It will only hold if there are no external forces acting on your system. But now you can object, because you say, well, let's make use of what we learned in the previous lecture. In the previous lecture, we said that if an object is changing its velocity, right? We talked about the uniform circular motion, then there should be a centripetal acceleration. The Earth is rotating, right, upon its around its axis. So if it's rotating about its axis, it means that there should be a centripetal acceleration acting. So whatever frame of reference I take here now, I say, okay, this is my frame of reference. It's this classroom here. You can say, this classroom is not good because there is a centripetal acceleration. You would be right. But let's calculate this centripetal acceleration. See how large or small this centripetal acceleration. We have all the tools now to calculate that. I want to remind you here, at the very beginning of in the first lecture, I think I said, that the way that the lectures go mostly is that every lecture will build upon what we've learned in the previous lecture, and we'll try to add more and more knowledge. So we use the previous knowledge in order to conclude new things. So let's use the previous knowledge. We have the Earth here. and it's rotating with omega. For simplicity, we take omega as the omega is 2 pi over the period, right? What is the period? It's 1 day, more or less. 1 day, this is 24 hours times 3,600. That would be in seconds now. So altogether, if I substitute there, we get omega, which is in radians per second. And that would be, whatever it is, 2 pi over 24 times 3,600. We are here on the surface. Our frame of reference is here. This is the classroom. It's on the surface. And we know the radius of Earth, which is about 6,400 kilometers. So there should be centripetal acceleration towards the center. That centripetal acceleration is omega squared times r. If you plug the numbers, you should get 0.034 meters per second squared. Let me leave this from here. Yeah, you just need to substitute. What is this? This is 300 times smaller than the gravity that the objects in this frame of reference would actually feel. So if my experiment has to do with this tennis ball, and you say, well, you can't really do it here because the Earth is rotating about its axis, and that adds some centripetal acceleration that you're not taking into account, I would tell you, well, that centripetal acceleration is 300 times smaller than the value of gravity, about 300 times smaller. And also you can consider the centripetal acceleration as a result of the rotation about around the sun, and which is there's a factor of 5 times even smaller than this. Okay, so can you ever prove that there is a frame of reference where there is no acceleration at all? Right now, we can't prove that. So why do we use the Newton's law? We know that if we, from experience, from all the experiments that we do, the experimental results are consistent with Newton's law, as long as you don't get to velocities that get closer and closer to the speed of light, and then it's a different physics. Okay, so we can say we're solving real world problems, right? Applied math problems, and we can neglect, this is a very small number, it's 300 times less than the gravitational acceleration. We can neglect this. Okay, so we believe in the second Newton's law because it's consistent with the measurements that we do. So F equals ma, we're going to use this a lot, and that will give, if you think in terms of units, this is in kilograms, so that the units would be, going to write them here, is kilograms, and this is meter per second squared, or we simply say Newton. These are these units, the force units, and note that the force is a vector. All right. So we know F equals MA. Let's do something with this and then move to the third law. I have the tennis ball here. I know that there's gravity here. F equals MA. So there should be some acceleration on this object. But if there's an acceleration, it should be standing still. So I'm holding it with my hand and it's standing still. And the question is why? Why is it standing still? F equals MA is telling me there should be some acceleration in the system. Yes. F is a vector, so you need to think of all the forces involved. What are the forces that are involved when we talk about this problem? We have gravity force, but there's also a normal force. So my hand is actually applying a normal force in the opposite direction on the tennis ball. So this is the tennis ball. There's mg. I could write ma, but a is g. So it's mg in the downwards direction, but there's also a normal force. Now we have to live with it. With normal force, normally we write n, but you know this is n for normal force, and it's not the unit Newton. And in this case, n equals mg. Or in other words, what is the total forces acting on this object? The total forces would be mg minus n, which is 0. And therefore, this is standing still, and the acceleration is 0. Now, in other words, I can write that the force of my hand is equal to minus the force of gravity. And that brings me directly to the Newton's third law. Newton's third law says action equals minus reaction. If I'm applying a force on the wall with my hand, then the wall is applying a force which is equal in magnitude on my hand, but is opposite in direction. So now you can understand this also using the third law. There are two opposite forces that are acting on the tennis ball: the gravity force, but also the gravity force. The tennis ball is applying a force on my hand, which is equal to that gravity force, right? It's the mg, m, the mass for this object. As a result, from the third law, my hand is applying a force which has the same magnitude, but exactly opposite in direction. So if I have two forces now acting on this object, and they are opposite to each other in the direction, these are vectors, you add them together, you get 0. So it's standing still, there is no acceleration. Okay. Make a simple example. We have two objects, the first object and the second object. Now, ignore gravity in this system. I have a force. This is the only force that applying on the that I'm applying on the object. Okay, so this is my force. I think it's from left to right. So it's a 1D problem. So I can just put it without the vector notation. But you can, let's put it now. Doesn't matter. Let's assume that I apply a force which is 20 newtons. That's the force that I apply on these objects. This object, M1, is 5 kilograms. And object M2 is 15 kilograms. Would these two objects start accelerating now? Yes. Why? Because the only force which is acting in this system, and this is what I said at the beginning, is just this force from left to right. So there is a force from left to right, which is 20 Newton acting on this system. In whatever state this system could be moving at velocity in that direction initially. As I start applying the force from left to right, from Newton's second law, the force is in the direction of the change of the state. Now the force is in that direction, so the objects would start changing their state, accelerating in that direction. So even if they were moving initially from left to right, from right to left, they would start decelerating, which means they're accelerating in that direction, and then accelerate in that direction. So all the time they would actually accelerate in that direction. What would be the acceleration? Well, one answer would be straightforward. You can say, well, in engineering, we say this is the system engineering view. You look at the whole thing as one thing. You say we have these two objects together. They are 20 kilograms, right? So if we have 20 kilograms, F equals ma. So M1 plus M2 times A, which is 20. M1 plus M2, that's 20 kilograms, and this is 20 Newton, right? So A is 1 meters per second squared. Now let's solve it in a different way to apply the other laws. We can just look at this object. So object number 2, why is it moving? Why is object number 2 moving? Well, object number 1 is applying a force on it. So let's call that force F1 acting on 2. So the force that object 1 is acting on object number 2. Let me just make this bigger for you so it would be in the same proportion here. So this is the object number 2. And object number 1 is here, and it's applying this force 1, 2. Okay, so according to Newton's law, F12 equals to M2 times A. Well, M2 is 15, right? It's 15 kilograms. It's here. And A, we found it's 1 meters per second. So this is 15 Newton. Now let's see if this satisfies, if we isolate object number 1, it should be consistent. So let's isolate now object number 1. So now this is object number 1. For object number 1, there is a force which is 20 Newton from this side. Object number 1 is applying a force 1, 2 on object number 2. So object number 2 should apply a force F21, which is exactly equal in magnitude. So it's 15 Newton, but it's opposite in direction, as I put it here. You can put the vectors here, but I put the arrows so you know it's in the opposite direction. So you know now, if I want to sum the forces on object number object number 1. So the forces on object number 1 would be F. I'm going to put the vectors now. F plus F21, which is 20 minus 15. Now, you can say, oh, why is it minus? Why is it minus? Why this is plus? Why is not the other way around? It depends on the axis, the positive axis of x. So if we choose x in that direction, being positive, then you would have a minus and a plus here. Otherwise, it would be in the opposite direction. And then the acceleration would be with a minus sign. But it would mean the same always. It means that the acceleration is in that direction. In this case, the acceleration is in the direction of the increasing value of x. So this gives 5, which is, what is 5? 5 is m1 times a, and a is 1. Okay. So we found that it is consistent that the mass of this object is 5 kilograms. So we solved it in one way, and we verified that you could also start like this and then find a from these two and then verify the other way around. Okay, let's move on. There are many quite intuitive problems related to Newton's laws. What do I have here? Unfortunately, I can't do this demonstration for you because of the space, and even if I try to do it like last time, it won't work with this, because the idea behind it is that I have this can. I make 4 holes in this can. There's 1 hole here, there's 1 hole here, and so on. So basically what you do, you can try this at home. So basically what you do, I'll take a cross section of the can, or top view if you want. You see a circle like that, right? So now you're looking like this. You make a hole here, and as you do it, you twist it to one side. So the hole actually is not radial, but it's actually going almost tangential. Okay, and you do it also here. So it's tangential like that, and you do it here, and finally here. As a result, you need to be careful, because here now goes like that, here is like that. You need to do it the other way, like that. Okay, you fill it in with water. You make the holes at the bottom, closer to the bottom. So this is now the can. You make it somewhere here, this line. You fill it in with water, and you hang it from a string. Now water starts going out from these holes. And then as it goes out from these holes, now action equals minus reaction. Water wants to go in that direction, here and here and here and here. As a result, the whole thing wants to go in the opposite direction, so it starts rotating. So you would have created an engine. I can't show it here because if I put it too close, then it's going to be too messy. And if I put it too far away, you won't actually see anything with the water. But you can try this at home. And I have something else here, which you can see. Action equals minus reaction. So we have this balloon. Now, you might laugh about this balloon, but this is the whole idea behind rockets. You have gases going out from one direction, and then the whole thing is going up in the other direction. Okay. Now let's move on to think more in detail about what do these laws mean. I'm going to do this through an example. Imagine there's a tennis ball. I'm going to show it to you soon, so we don't have to. So you have a tennis ball. This is a tennis ball. And this is the surface of Earth. I take this tennis ball 10 meters, 100 meters away, and I let it go. And it starts falling. It falls, and as it falls, it accelerates. Now we're ignoring the friction, we're ignoring assume that there is no air. So it's just accelerating, and now you know how it accelerates, right? You remember the monkey? Half g t squared from kinematics, half g t squared. So if I just leave it, assuming that this is my x equals 0 there, right? So I don't have an x0 here. I know g. I can calculate the time that it would take to reach the ground, knowing that I know the distance here. Now, normally when we talk about the distance in the vertical direction, or many times we simply write h for the height. It's the same thing. It's the distance. So I say we have the tennis ball, which is here. And I'm standing here in this room here. Frame of reference is actually this room. And this is, let's say, 100 meters. Can I go much higher than that? Can I go 10 kilometers? And still use this? I can go 10 kilometers. So the question is if I can still use this equation, this relation. I can't, because g is constant, right? In this relation here, it is constant as long as you're close enough to the surface of Earth. But it's close enough, you would have the opportunity to calculate that later on in the module if we get there. But if I go too far away, then g becomes smaller and smaller and smaller. Remember the problem that we solved with the space station, with the donuts, right? Which is rotating. As you start going inside and inside, closer and closer, it's similar in that way. The gravity, the perceived gravity, becomes smaller and smaller and smaller until it goes to 0 in the middle of that donut. So the analogy is similar here. So if we go much farther away in kilometers, g becomes smaller and smaller, and we cannot use this anymore. So g would be changing due a function of the distance. But here we're safe. 100 meters, it won't matter. It's still about 9.81. Okay. So 100 meters equals to half gt squared. So from here, we can calculate the time. So the time is about 4.5 seconds. If there was no air, falls and keeps accelerating, then it would reach the ground in 4.5 seconds. Now, later on, when we get to drag and friction, you will see that this will never happen. Okay, but let's leave it for that time. So this is the time that would take the ball to reach the ground. But Newton tells us that action equals minus reaction, which means who's falling on whom? Is it the tennis ball falling on the earth, or is it earth falling on the tennis ball? Now think about it, it's not very intuitive, but in fact, they're both falling on each other. It takes 4.5 seconds for this to fall there at an acceleration which is g, 9.81 meters per second square. How long will it take for the earth to fall on the tennis ball? Same thing. It takes also 4.5 seconds for the earth to fall on the tennis ball. But what would be the acceleration? Let's calculate that. Now, how would we calculate that? F equals ma, Newton's second law. F equals ma, and now we write, so this is the forces for earth. Oh, earth equals ma, the mass. We want to find A. This is what we want to find. So we can write A equals F over M. And these are for F. What is F? We need to go back to the tennis ball. F for the tennis ball, right? Well, FB is for the ball equals MA. Let's assume that this is a, I don't know, just for simplicity, let's say that the whole thing is 5 Newton. Okay, so it's a very big tennis ball. Okay, it's a half a kilogram. So this is a half kilogram. This is about 10, right? This is G. So it gives about 5 Newton. You will see that why I'm doing this roughly, it doesn't really matter, because once you plug the numbers here, so this has to be equal. F is the same, right? It's just opposite directions. So F of this and F of that are the same. They're just opposite in direction. This would apply F on this, and this one would apply F there. So we have 5 divided by what? Divided by the mass of Earth. And that is quite a lot. It's 6 times 10 to the power 24, which means that the acceleration of Earth would be a very small number, is 8 times 10 to the power minus 25, something like that, meters per second squared. So now things become sound reasonable. Yes, this is falling on that, right? The Earth is falling on the tennis ball, and the tennis ball is falling on Earth. It's just the acceleration of Earth is so small, right? It falls at this acceleration that you can't even measure it. It's very small. In fact, if I have the tennis ball here, maybe it would be more convincing first to think about these two objects in space. So as this is falling on, as the tennis ball is falling on the basketball, right? Let's see, this is the midline, okay? They will meet there, okay? So they start something like this. The acceleration here is much larger. It falls like that. Now I do it, it falls and bounces back, because I'm going to show you something soon. But this is the idea, all right? But now think about it as an Earth. So the acceleration is much, much smaller than we can't even measure it. But the idea now is that if I have this object, or the basketball, every time that I threw the basketball up, right? So I have to apply a force upwards when I throw this up. It means that I'm applying a force on Earth. I'm pushing the Earth downwards. So every time that I threw this up, I'm pushing also the Earth down. By how much and what are the times? The times are an agreement. It takes this to go up as much as it would take the Earth to go to the opposite direction. But how much would this move? Well, as much as I can throw it up, and it would go with some acceleration. But the acceleration in the Earth and in the movement in the Earth is so small that we can't even measure it. So now things are back to proportion. Okay. Now, what happens if I take an object and hang it on a string? I have an object and I hang it on a string. F equals ma. Okay, this is the floor here. It's not touching the floor. And it's in this rule, and there's gravity, and the gravity is acting downwards. I know now that mg, this object would feel a force mg downwards, but it's just in place, right? It's not accelerating downwards. Why? Because there's another force which wants to push it upwards, and that force comes from the tension in the string. So there's a tension here, T, and that tension is equal to mg. And therefore, if you now apply Newton's second law, F equals ma, let's do it properly. Let's assume that y is in that direction. Okay, if y is in that direction, so my t here is in a plus, we sum all the forces, right? All the forces would give me this F here. So it's T minus mg equals ma. So the acceleration in the object would be equal to T minus mg, but we know that T equals mg. So this is 0. So A is 0. Now let's think a little bit. What happens if, well, let me ask it in a different way. Should the tension be the same everywhere in the string, or can it be different from one point to another? If the tension was different, if the tension in the string was different, so this is T, but from one place and to another. So if we take a small element of the string, on that element, again, you can apply Newton's third law, action equals minus reaction. From one side of it, this is something I want you to understand very well. So this is a small element of the string. So if I do something like this, okay, this is an infinitesimally small element of the string, which means that here, if it was some T1, and here it's T2, and T2 is not equal to T1, what would happen is that, no need to guess, look at F equals ma. Now F here is T2 minus T1, or T1 minus T2 if we use the y in that direction, right? T1 minus T2. This is a small element which would have some finite tension, because T1 minus T2 is not 0, if we assume that the tension is not uniform everywhere. but the mass of this element is very small, right? So we have a delta m, and this delta m goes to 0, which means the acceleration in this system, if you take the limit where delta m goes to 0, the acceleration would go to infinity. What would happen to that string? It won't survive. And therefore, as long as this is the case and it's hanging still like that, it means it has to mean that the tension everywhere here is T and it's the same. It's not, there's no change in the tension. I hope you understand this, because that should help you. And you need the understanding in order to digest what I'm going to show you next. I'm going to make an experiment. In this experiment, I will have some mass. We have a mass, and that mass is hanged with some string. There is a second string at the bottom here. And my question is, what happens if I pull this string, the bottom one? So there's some mass here. And I pull the string, the bottom string here. So this is the upper. And the question is, what would happen? What do you think would happen? Would it be cut here, or would it be cut here if I keep pulling and pulling and pulling until the string cannot hold the force any longer, right? Each string would have a limit in terms of the force. Would this one fail, or would the upper one fail? If you think the lower one would fail, right? The lower one, or just L. If you think the upper one would fail, write the upper one. If you're not thinking about any of these, then just write down your intuition. What would happen? I mean, if you're not thinking in terms of what I explained about. Okay, I give you a few seconds to think about that. I see upper, okay. Anyone thinks lower? I didn't see all the... All right, let me just explain what's this. The yellow string here is just for safety, just in case you're right, whoever said the upper one, there is a yellow string, which is a safety string, is not taking any of the, let me move this a bit. Okay, it's not taking any of the tension. It's just for safety. So if this fails, the upper one fails, it won't fall on the floor. Okay, so this would be my yellow string here. This is just for safety. And I have a blue string here, which I'm going to put up now. It's at the limit. I hope it won't fail before I start the experiment. It could. Otherwise, I would have to well, I have one already prepared just in case. But okay, let me put this gently. I have here 1 kilogram. It's a little bit maybe too heavy for this type of string. But what I want to mention is that there's a string here. Maybe you can't see it. maybe now you see it, it's a blue string. Yeah, it's gonna be in full tension soon. And there's another one, and there's another one here, down here, there's another string. I put this just to help me to pull the two together. Okay, let's put it in a way that you could actually see. So let me take the whole thing up. This is one of the places where it would be useful to have some help, more hands here from the from the students. All right. Okay, so I'm going to slowly release this. Let's put it maybe in this way. Yeah, that's better. I'm going to slowly release this. Hopefully it won't be cut because this is too heavy. This one it won't be cut right now. It won't fail right now, right? Anyhow, the question is what happens when I start pulling. Now let's see. I feel it's going to fail before I start. Don't fail. Okay. All right. So right now, okay. 1 kilogram is a little bit too much for this. I'm gonna try it again. It's my excitement, I think, added to the tension. All right. Let's do it again. So whoever thought that the first one is going to fail, that doesn't mean that you're right yet. Okay. Okay, no movement. Okay, I'm gonna start almost immediately because you see this? You see this? So the lower one failed and the upper one is hanging on. Now, let's do it again. Why is that? Now you need to rethink. I'm gonna redo it again. I'm gonna redo it again. Now you know what's gonna happen. So what's gonna happen? Please type what's going to happen. Is it the lower one is going to fail or the upper one is going to fail? I'm gonna do it in a few seconds before that fails anyhow, from my excitement. So just type down, you've seen already what's gonna happen, right? Here we go. I still have some part of the lower one, so I'm just going to pull it with my fingers. Well, I can do it the same as before, so just for the third testing. Okay, which one is gonna fail? if you don't see, there is a string here. Some of the lower one would fail now, right? Because you've seen this already, right? Now look at this. I'm gonna start now. Ready? Go. Ah, the lower one failed. Okay. Why is it that the lower one fails? I'm gonna do it one more time. One last time. So everyone, I'm convinced that the lower one will fail. Okay, there we go. Oh, what happened? The lower one didn't fail. It's the upper one which failed. What's going on here? So first time, the upper one failed. Well, it failed by itself. That's not counted. So the first time, the lower one failed, and then I repeated that, and then the lower one failed again. And now everyone was convinced that the lower one is the one that would fail, and then the upper one failed. What happened? There's no magic here. There should be some physical explanation, and the explanation has to do with what I put here, but also you need to think also about the fact that you have this kind of system. I'm not going to tell you the answer. I want you to think about it yourselves. Okay, so we're going to stop here. By the way, do we have the visitors there now? If they I guess not. So, okay, very nice, all yours now. I'll see you next time. Thank you.
Hello, everybody. Feel free to take 5 minutes of break. So I'll start at 2:07, okay? Also, feel free to ask me any question in those 5 minutes because I will be around. Okay, hello, smart people. Are you all doing well? So I remember that the other day I didn't solve the last part of the last exercise, right? Where we are asked about drawing some charts related to the motion of the object. It is the exercise 3.21 of the third assignment. Okay, guys, so have a look at it. So first of all, we are asked about calculating the maximum height above the roof. So what's happening here is that a man stands on the roof of a building and throws a ball with certain angle with respect to the horizontal, okay? This ball reaches a maximum point and then falls, okay? We have gravitational acceleration, and we set our reference frame in the position of this man throwing the ball, okay? So we consider x positive towards the right, y positive above the building, okay? So we calculated the y maximum and we calculated the final distance, xf, okay? And we are asked to draw. Okay, what are we asked to draw? We have to draw a xt chart, which is going to be this one, yt chart, the velocity in x, how it changes with respect to the time, and the velocity in the y direction, okay? So we will start first of all, this is a very conceptual part of the exercise, okay, guys? So I really want you to understand what's happening here. So we have to draw how the x position changes in time, okay? So it's gonna start in 0, right? Because we consider our reference frame at the very beginning of the trajectory of the ball. And it's gonna grow with a constant speed, but we don't have any force or acceleration in the x direction. So it's gonna grow linearly. This is important to understand, okay? So this is gonna be our x chart. So if we don't have, as we have seen today, if we don't have forces, we don't have acceleration. Force and acceleration are related, okay? So if we don't have acceleration, we are gonna have a linear motion, which can be, if the object is still, it would be just an horizontal line. But we have an initial speed. So if we have speed, it's gonna grow linearly. What happens with the y position? Well, where do we start? We start at 0, okay? Because we set our reference frame here. So we start at 0, and it grows linearly or not linearly. What do you think, guys? Do we have forces acceleration in the y direction? What do you think? Non-linearly, non-linearly, okay? Because we have acceleration, okay? So we have the gravity reducing our speed, okay? So our position might do something like this, right? Or if we are seeing reduced, something like this, okay? So let's say that, for example, we have it growing like this, okay? Up to the maximum height, y maximum. Does this make sense to everybody? And then we have to find what is the final position, because we haven't found the final time, right? So, and it's gonna cross our reference frame. So we might end up here, okay? Considering that this is h and this is our y maximum. This or this? What do you think is gonna happen? If the speed is growing as a multiple, it might happen something like this, right? Does this make sense to everybody? How this is growing? Okay, we have the X chart, the Y chart, and now we want the velocity, okay? The velocity in the X direction is not affected by any acceleration. So it's gonna remain constant. So it's gonna be an horizontal line, okay? Situated at V0x, not V0, because we are decomposing the initial speed in X and Y, important. So we have Vx0. What happens with Vy? Well, now we do have acceleration. So we know that acceleration is gonna be equal to the derivative of the speed with respect to the time, okay? In the same way that we know that the speed is the derivative of the position with respect to the time, okay? This would be Vx, okay? Because we are differentiating X. So how is the speed gonna grow? Linearly, non-linearly? How do you think it's gonna grow, guys? We know it's not starting at 0. So we know we have an initial y speed. So it's gonna start here. So this is something that we know. And what else do we know? Well, we know that at y maximum, we're gonna have 0 y speed. So it's gonna go from here to here. And then it's gonna grow due to the gravity. Linearly. It's gonna grow linearly. Okay? Oh, you can't see what I'm writing. Oh. Can you see it now better, guys? I don't think I can do much better than that. Okay, that's wonderful. What I was explaining is that the y speed is gonna start at v0 in the y direction. It's gonna reduce up to 0 because we know that at the maximum point of the trajectory, the speed in the y direction is 0, and then it changes, okay? So it changes sign, okay? Because we know that the velocity is a vectorial quantity, okay? It has some direction associated to it, okay? So we start as positive, we reduce up to 0 linearly, and then we are gonna start having negative velocity, increasing negative velocity, okay? So this is our V0y chart, okay? And what about the acceleration charts? Those are not, you're not asked about those, but we can draw them easily, right, guys? Because you know that, for example, the acceleration in the x component of the acceleration is 0, and it's gonna remain 0 all the time. And what about the y component of the acceleration? Well, we know we just have gravity. Okay, that's right. That's perfectly right. And actually, I wanted you to spot this. Okay, wonderful, wonderful. Why do we know it's a parabola? Well, we can deduce that by differentiation. Okay, but yeah, that's a really, from the equations, exactly, from the equations. That's a really good point, and thanks a lot, George, for pointing out that, okay? So it's important, guys, that you know these type of things because they are very conceptual and they are gonna demonstrate that you understand what you're doing. Let me finish just here in G, is constant. So what do we know? Well, we know that when we have a force, the position is gonna change non-linearly. That's important. The shape that we want, in this case, is a parabola, okay? From the equations, we know that. What else do we know? That the velocity is gonna, in our cases, change linearly if we have a constant force, okay? Because we are assuming that the gravity is a constant force. So we have a constant acceleration, okay? So the velocity is growing linearly because we have constant acceleration, okay? If we have a varying acceleration, the velocity might grow as a parabola as well, or as a hyperbola. That's really important. And yeah, I'm very happy to have really smart people spotting my mistakes. Great. Okay, guys, so I just wanted to point out these things because they are really, really important. This was the most important part of the last assignment because it's very conceptual, okay? Okay, wonderful. So I don't know, do you have any question, guys, about the exercises, any of the solutions? Some of the solutions I provide might have mistakes that you might be able to spot. So feel free to raise them here in the tutorials, okay? There might be some traps, or maybe not. So that's why I want you to ask questions. Okay, so I will start doing a small summary of the lecture today. Basically, we have gone through the Newton laws of motion, which are 3, right? So the first one is gonna say that an object that doesn't experience any external force is gonna remain either still or at a constant speed, okay? What does this mean? This means that, for example, an object that is still, for example, this ball, the summation of the forces acting on this ball, because the ball is still, we know is 0, okay? If, for example, we know that the ball is accelerating, in such case, this summation of forces wouldn't be equal to 0 because there is some acceleration over the ball, okay? So forces mean acceleration. If there is no external force, there is no acceleration. So the ball would keep at a constant speed or still, okay? So this means that the object is in equilibrium, okay? The second law relates mass with force, right? So we know that force is equal to mass multiplying acceleration. What do we extract from here? We extract that force scales linearly with respect to the acceleration, also linearly with respect to the mass, okay? So the same force for two different objects is gonna have two different accelerations if the mass differs, okay? That is important. And the third law is gonna be related to normal forces, okay? What probably you already know from experience, past experiences. For example, you shouldn't punch a wall, okay? We all know that because the wall is gonna punch us with the same force. So we know that an object, for example, let's say this brick with a mass m, is gonna exert the force of mg over the ground. And in the same way, we know that this object is still. From the first law, we know that the summation of forces is gonna be equal to 0. So mg is gonna be equal to some normal force. We need a normal force to give sense to this problem, okay? So those are the 3 big concepts that I want you to settle and know. I don't know if you have any question about those things, guys. Yeah, basically that. Well, we also know, I want to point out also that we know that acceleration is the derivative of the speed with respect to the time, right? So we know that the force is gonna be this, okay? So if we plug this in here, we can again verify that from this in here, because we know that if the summation of forces is 0, it means that the derivative of the speed with respect of the time is 0, which means that the acceleration is 0. But if we have a resulting force, if this is not 0, we have some resulting force, we know that we are going to have change of velocity with respect of the time. So the velocity is going to change in time, okay? Another of the things that I want to mention is that the international unit of force that we're going to use is the Newton, okay? The Newton, okay, important, which is defined as kilogram m/s squared, okay? So it's the force that you will have to put on a kilogram of mass to make it move at this speed, 1 meter per second squared, okay? So we have acceleration, we have mass. It's very obvious, right? And we can know this from the equation that we have already written. Force is equal to mass multiplying acceleration. So the units of force are going to be kilograms multiplying meter per second. But to make this easier, there is a consensus amongst the scientific community to call this Newton. We all know why are we calling this Newton, right? So those are the major points of the. Yes, yes, exactly. So do you have any question, guys, related to this? Or related to the lecture today? Do you have any question that you would like to raise or create any debate here to talk about? Or you are happy with the concepts? Okay. About the experiment, well, I believe that Usama wants to talk about it in the next week, so I don't want to do spoilers about it. Acceleration. Okay, so that's a good question about the acceleration, right? You are talking about centripetal or radial acceleration. So we will talk about it now. I'm gonna solve some problems related to it, and we are gonna talk about it now. And in regards to the tension, I think it's something that you have guys to figure out and sit at home and think about it. And Usama is gonna solve in the next lecture. So I don't want to do spoilers, but you can start thinking about normal forces. For example, the tension force from a rope is a normal force, right? That doesn't exist if I don't apply an external force to that rope, okay? So it's basically a reaction from the rope, okay? So yes, I will go through the centripetal or radial acceleration, okay? Well, of course, inertia is a really important concept that is going to help you to approach all those things, right? Because, for example, we know that force is equal to mass multiplying acceleration. And this equation comes from a change in momentum, okay? Which is related to inertia, okay? The momentum and inertia are very related. So that could be a good approach for the problem, or for any other problem, to having inertia in mind, okay? And we all know that inertia scales with mass, okay? So that's a good point. That's a good point. So in inertia, you're gonna see it very soon, guys, because it's very related to Newton's laws of motion, and some of them come from changes in momentum. So that's a really good point. But again, I'm not gonna do spoilers. Not this time. Okay, so what exercises did we have to solve? They were 3 easy exercises, right? I really believe that, guys, you tackled them like a completely masters. Okay. 3.25. Oh, I think Usama has solved this exercise today. He did my job. this exercise in the lecture. If you realize, he was talking about the gravitational forces at the surface of the Earth. Okay, so we know the radius of the Earth. We are gonna assume that the Earth is completely round. We all know that the Earth is not completely spherical, but it's a really good approximation, because if you think about it, what are the biggest differences, right? How high is the Everest? It's 8 kilometers, or the Mariana is one of the deepest points in the ocean, is 11 kilometers deep. So 11 kilometers with respect to more than 6,000 kilometers radius is a really small change, right? So we do believe that the Earth is almost spherical, and also the difference between this radius and this radius is very small. It's very small. So the Earth seen from the space is like a completely perfect ball. Okay, even though we know it's not. Okay, so we have the radius. Let's assume we have the radius, and the radius is constant all along the perimeter. Okay. And we want to know what is the, well, we know the period. So we want to know what is the radial acceleration. Okay. So this is related to the question that I just received, that where does that omega multiplying r come from, right? Let me have a look, because I might have some hints, or maybe not. But okay, so we have a tangential speed, right? And we know that to do a completely loop, we have to cover 2 pi radians, okay? Because the full circle is 360 degrees, is 2 pi radians, okay? So we can say, okay, my angular speed is gonna be equal to the time that I take to complete 2 pi radians. We know that the units of the angular velocity is radians per second, or they can be degrees per second, right? But it's more usual to find radians per second. I find also way easier to work in radians, and I strongly encourage you to work in radians, guys. Okay, so we know that we have to cover 2 pi radians in one period of time. Okay, we understand this. Then what we assume is that we have this tangential speed that is constant in our case. Okay, let's imagine that it's constant. V, the same speed all along. So if we consider that at this speed we are covering the perimeter, we can relate that to the angular speed, okay? So we can basically say that my speed is gonna be 2 pi r, which is my perimeter, right? Divided by the period, okay? So the period, sorry, is gonna be, this is more intuitive in the other way, 2 pi r, okay? If this makes sense, right? So we know the tangential speed and we know the radius, so we can calculate the perimeter, okay? So we can calculate how long am I gonna take to cover the whole perimeter, okay? So I can calculate the period, if it makes sense, guys, okay? And then we know that 2 pi t, we can plug this in here, okay? Because we know that the angular speed is equal to 2 pi divided by the period, okay? So we know that the velocity, okay, if this comes here, is gonna be equal to WR. Okay. Does this make sense? Huh. Yeah. So far, I was able to obtain and relate angular speed with linear velocity, okay? And now we want to know what is the centripetal acceleration, okay? And now you get me about where exactly does it come from. So far, I just know that it's equal to W squared R. I believe that it might have been explained in the previous tutorial, guys. So I will have to take a look to where does it come from. I'm sure it's in the book. Let me have a look to the book. So where it exactly conceptually comes from. Motion in a circle. Okay. So basically, the acceleration is going to come from a change in speed with respect to the time, right? So that centripetal acceleration yeah, it was derived in the last week's lecture. Fair enough. Okay, fair enough. So basically, that's very conceptual, and this is only for uniform circular motion. But yes, it's basically you take the limit. Yeah, you have to differentiate that. Okay, thanks, George. You are doing the lecture or the tutorial for me today. Yeah, I owe you one. Okay, great. So we know this. We can calculate the centripetal acceleration at any point if we know the radius and the angular at the angular speed. Okay. Yeah, basically that's everything. I don't know what is the question asking us. Let me see what was the assignment. Find it. Lost it. What is the radial acceleration of an object in the Earth's equator? Okay, we can calculate it with that formulation because, as I mentioned, we can obtain this from this equation. We can obtain the angular speed from here and then plug it in here again. What would be the period of Earth rotation in order to overcome G? Okay, so basically we have done this today with Usama. Okay, guys, I have it somewhere here. I believe, or maybe not. So yeah, we know that the radial speed can be calculated also from the tangential speed, right? Because we know that it's also v squared r, okay? We can relate this with this through this, okay? It's all about being a bit creative, guys, and working out. Okay, I have it in the other way around. V, do I? Okay. Maybe I have it wrong, guys. Let me see. Oh, what a day, eh? I'm just missing everything. Okay, let's have a look. Yeah, I believe you. So I might have it everything wrong. W squared. So we know that this centripetal acceleration is W squared R, right? I also think it's okay, but we are gonna try to see if it's wrong or not. Okay, so we know that, okay, that the centripetal acceleration is equal to the angular speed squared multiplying the radius, okay? We know that the angular speed is 2 pi divided by t. Conceptually, we know that, it's obvious, okay? So if we plug it in here, we know that AC is equal to 4 pi square t square r, okay? Which coincides with the book's definition, okay? I don't know what is wrong. What do you believe is wrong? Sorry. V is the linear speed which is in circumference, which is the circumference divided by the period. Yes, that's right. That's completely right. Yeah. I agree with those things, but I don't know what exactly in the board is wrong. So I can try to. Is this wrong? Or this? What do you think is wrong? This? I also can't see what is wrong. So if a J could help me, I got 2 pi r divided by v. Where do you have that? Oh, the top equation, this one. Okay, so we know that the period is equal to okay. Okay, so the linear speed multiplying 2 pi r conceptually is the time that I would take. Does this make sense? Oh, yeah, that's completely right, divided by v. Okay, that's completely right. I took long to understand that. Okay, divided by the speed. Okay, distance divided by speed is equal to the time. That's completely right. You were completely right. This was wrong. And conceptually, if you think about it, basically the circumference or the perimeter, 2 pi multiplying r is all the distance that I have to cover linearly, which divided by the linear speed is gonna give me the period. That's completely right. I was wrong. Yes, thank you. Thank you for pointing out those mistakes. Okay, that's great. So, okay, now we all understand circular motion, and I verify that you understand it, guys. No, thanks to you for spotting the mistake. It was a really good observation. It was a really good observation. Very intuitive and very good. Okay, so basically this is most of what we have to know about circular motion, guys, okay? And we can solve the problem with this. Did you have did you struggle to solve this problem? Did anybody struggle to solve this problem? So this is how I solved it. I basically say, okay, my radial speed is equal to v squared divided by r. So I can obtain my centripetal acceleration. Always is pointing, the centripetal acceleration, it always points towards the center, okay? So, or in this case, outwards, because we don't have a rope, we don't have anything attaching it, but we consider it towards the center, okay? Always towards the center. V divided by R, we know V, we know R. Do we know V? No, we don't know V. So we have to calculate V, okay? And we calculate it through this equation, okay? Where we know that 2 pi R divided by T is gonna give me V. I encourage you to work in the international units, okay, which are meters per second. So if this is 24 hours, would be 24 hours multiplying seconds per hour, 3,600 seconds per hour, and you work 2 pi r, but the r is 3,600 or 6,300, is it? 6,400, let's say 6,400 kilometers, but I want to work in meters, so I say that 1,000 meters is 1 kilometer, and then I obtain my solution in meters per second. Okay, so once I know this velocity, I can obtain my radial speed in meters per second square, and I'm asked to give my answer as a fraction of g. Okay, so how would I give a fraction of g? I can just multiply and divide by g, right? So let's say I have that the radial is 0.4 meters per second, Osama said, I believe. So you just multiply and divide by g. Okay, and this number is the g's that you have. So then you say, what would be the period of Earth rotation have to be for this to occur? So intuitively, we know that the period would have to be smaller, so we have higher speed. Okay, guys, so we can basically just plug this. We need a higher acceleration than that, so we just have to obtain the new period. Okay, so we can say, okay, my radial speed is equal to this 2 pi r t, all this squared, divided by the radius. Okay, and from here we can obtain what is t. Okay, so we just basically take t out of here, and we know that we will need a higher acceleration than 9.81 meters per second square. We would need higher than g, so we would need that this to be bigger than 9.81 meters per second square. Okay, so we can obtain t. Okay, although all those exercises are very similar, I don't know if I think the time is gone. I'm sorry, I made some mistakes today, guys. I don't know if you have any question about the exercises. I can spend 10 more minutes trying to solve any question that you have about the exercises. Guys, does anybody have a question? Yeah, sorry for the mistakes, guys. I took some of your time solving them, so I'm happy to stay here a bit longer if anybody has a question. I should release them before tomorrow night. Yes. By the way, I don't know, I haven't repeated it again, but do you want to suggest any exercise? If anybody has looked, or do you want to spend 5 minutes looking to the exercises and suggest any exercise? I will solve them for you guys. I will put them in the assignment and solve them for you. So feel free to suggest exercises that you might find difficult. If you don't find them now in 5 minutes, feel free to mail me with those exercises that you want to suggest for the set. Okay, and if they are too many, I will just select 3 of them. But I want to maximize your learning, so I would like you to participate more actively in this. Okay, that's fine. Thank you, everybody. Okay, I guess I will close. Feel free to mail me with anything. Diolch, everybody, guys, and have a nice week.